Hi guys, so in this lecture we'll be comparing stability um, of various organic compounds. So let's start with putting the question. So compare stability. So I'll be giving you 2-3 compounds and you have to compare the stability, relative stability among them. So we have something like positive charge here between this and so as you can see, okay, let me add some more compounds as well. Two plus and CH2 double bond CH. Okay, so you know this compound is aromatic. Why? You know the order of compare of um, this order HPCD, by which you can actually say whether the compound is aromatic or not. So Huckel rule is valid in this case because we have 6 pi electrons and it is planar. It is a cyclic compound and delocalization is there. Hence, this would be the most stable compound because it's aromatic. Rest other compounds are non-aromatic, okay, because simply they are not cyclic. Now we can see that in this compound, between this compound and this compound, more resonance is there in this compound because 3 pi bonds are conjugated with this positive charge, and in this case only 1 pi bond is conjugated. And again, between these 3 compounds, again we have, for comparing the stability of any 2 compounds, we follow the rule which is known as AIIMS rule. So according to AIIMS principle, we can see that for A its aromaticity, E is equivalent RS, R is resonating structures, and for comparing resonating structures, we have to again look into the rules which are more covalent bonds. I'll just write it in short form only. So for comparing the resonating stability of 2 compounds, first we have to see more number of covalent bonds, then we have to see the complete octet on the most electronegative element must be there, atom must be there. Third should be that the overall compound is neutral or less charges, and fourth would be obviously the negative charge should be on more electronegative element. Okay, H is obviously hyperconjugation, I is obviously inductive effect. So we, on these principles or on these rules, we compare the stability of any 2 organic compounds. Okay, so aromaticity we have already discussed that only first compound was aromatic, hence first is the highest priority, highest stable compound. Second, equivalent RS is not so equivalent. If you see the equivalent RS, so you can draw that, you can see that it has only 2 equivalent RS, and in this case we can see that there will be more than 2 equivalent RS because it is the exact number you can draw and check out which has more number of equivalent RS, but this would obviously have more number of equivalent RS because it has 3 pi bonds. Okay, now equivalent RS is also there. Now in between these 4 compounds we don't see any resonance stability rule, so it is out of the question. Now comes the hyperconjugation. So the hyperconjugation, as you can see, that it has 9 alpha hydrogens, it has 6, it has 3, and it is formation of, it is a vinyl carbocation. It is highly unstable. So this would be the order. Okay, let's do this for second example where we have positive charge here and O minus here. then we have CH2 plus and NH2 here, then we have CH2 plus and a methyl here, then we have CH2 plus and ethyl here, we have CH2 plus and this here, then we have tertiary carbon atom as a substituent to the phenyl ring, and finally we have this here. So now we have to compare the relative order of stability. So now let's see that on the phenyl ring we have a plus M effect group, which is the O- group attached to this phenyl ring, which carbon atom is attached having a positive charge. Hence this will be the most stable because of the plus M effect. Now between these two, in the resonating structure, N would have the positive charge here and O would have the positive charge here. Okay, and the positive charge on more electronegative element is less suitable. Okay, and positive charge on less electronegative element would be more stable. We are comparing between this and this, hence this would be more stable because this can bear a positive charge on itself. It is relatively more stable than positive charge on more electronegative element, in this case oxygen. Okay, in this case we are having 3 alpha hydrogen. This is more stable. This in turn will be more stable than this compound, which is having only 2 alpha hydrogen. It is having 0 alpha hydrogen. It is having 1 alpha hydrogen, and it is having 0 alpha hydrogen. So the order would be here this, and this NO2 group is act as a minus M group. We already have a positively charged carbocation on the top of a phenyl ring, and on the top of it we have a minus M group. It would be the least stable. Okay, now comes the third example. We have something like this, a bicyclo compound, this and this. So in this case, what would be the order of stability? And let's suppose we have a positive charge here. So according to the German scholar Bratz, this compound cannot even exist. Forget about the stability. So it would be the least stable because sp2 hybridization on the bridgehead carbon is for a cyclic ring or a bicyclo ring less than or equal to 8 member, it is highly unstable. Okay, and between these two we can actually have resonance between positive charge and double bond. Hence 2 would be the more stable, then 2 would be more stable than 3 followed by 1. Okay, so now in the below example you have to compare bond length. Okay, so next question is compare bond length, and you already know that more is the bond energy, less will be the bond length. So bond length is inversely proportional to the bond strength or bond energy. Okay, so we have first example has something like we have to compare bond energy between these three, bond length between these three. And which bond length we are talking about? The bond length between oxygen atom and this carbon atom. I'll just show you. We are comparing the bond length between this oxygen atom and this carbon atom in all the three cases. Okay, so as you can see, there is an extended conjugation that can occur in the third example. Hence this CO bond would have more sp3 character because of formation of single bond. Okay, and a negative charge on O minus. So the third bond energy, the bond length for the bond between the single bond between C and O would be the highest, and then followed by 2 and then 1, because and 1 actually has just double bond character and has the maximum double bond character. Hence more the double bond character, more is the bond lesser is the bond length. More is the single bond character, less is more is the single bond character, more is the bond length. Okay, now let us compare between this. This is the first compound and this is the second compound. Okay, so now as you can see that oxygen, because of a presence of lone pair on itself, will actually involve itself into the resonance, thereby creating a double bond character between this carbon atom and this oxygen atom. Hence, due to possessing double bond character, the bond length would actually reduce itself. Hence the bond length order would be 2 would be more than 1, because 2 is already a single bond. There is no scope for double bond character in this compound, because there is no lone pair pi electron conjugation. Okay, next let us compare between this and this. So as you can see that in this benzene ring we can have resonating structures, so there would be a partial single bond character also between CC bond. Okay, so single bond character, as the single bond character increases between a bond in a bond or in between two atoms, more would be the bond length. Hence this compound's bond length would be more than this compound bond length, because this is a static pi bond and it will never be in resonance, so it would actually be having more double bond character. More the double bond character, less is the bond length. So why should I should make some note here that bond length is actually directly proportional to single bond character and bond length is inversely proportional to double bond character. Okay, so this is the rule of thumb here which we should follow for answering these set of questions. Okay, let us look at the fourth example. Here we have phenol, and second case we have phenol and the carbaldehyde group also aldehyde group also attached. So what would be the order of bond length in this case? So the bond length would be of order this. Why? Because this is a minus M group. Okay, and as the minus M group is attached to the phenyl ring, the more electron density would shift to this oxygen. Okay, and as the more oxygen density shifts to this oxygen, there would be more double bond character between this carbon and oxygen bond. Hence more double bond character, less is the bond length. Hence second compound's bond length will be lesser than the first compound's bond length. Okay, let's take this example. We have this, a simple 2-degree amine and then a aniline. So obviously this has a double bond character because of its plus M towards the benzene ring. Hence as the double bond character increases, the bond length would be the least. Okay, oh just a case here. So the bond length character for in this case, when we compare this and this, actually this has already a bond length, a double bond character between itself and the carbon atom, so its bond length would be the least, then 3. Why? Because this is a resonating structure and this exists on real. This is a real pi bond and this would have some single bond character also. Although it is showing plus M, but it would have some single bond character also. Only in the resonating structure it would be delocalizing its lone pair towards the phenyl ring. Okay, but this is a static pi bond. Hence the static pi bonds bond length would be the least, then third, and then second. Okay, what about this compound? This is aniline 8. Let's compare between A, this is the B, and the bond between C and C is C. So the bond length order would be B, then C, then A. Why? As you know that aniline 8 exists as a tub shaped structure, so in the previous lectures you can see that the bond length B would be having the most single bond character, hence B would be the having highest bond length. Then we need to compare between C and A. So you can see that in the aniline 8, as the compound is non-planar, so it will not be getting involved in resonance. So unlike these pi electrons or pi bonds between carbon atoms which were actually involved in resonating structures, hence they are having more single bond character than the carbon bond in aniline 8. Hence C would be having more bond length than A, because C bonds carbon atom are actually involved in resonance. Okay, so due to the same reason they will be having more single bond character. Okay, let's look at the last example. We have this and O negative here, and we have to compare between this. So we have A here, B here, C here, and D here. So you have to tell me the bond length order. Okay, so as you can see that these two compounds will be having same order of bond length or same bond length. Why? Because of equivalent RS. Okay, because of equivalent RS, A and B's bond length would be the same. Okay, now we have to compare between D and C. Okay, so you can see that although the lone pairs are actually involved in resonance, but we will get a positive charge on this oxygen atom, due to which although it would show some resonating structures, but not in the extent it should show, because in the resonating structure this oxygen atom actually gets a positive charge, which actually make it slightly unstable to have a positive charge on itself, because it is a electronegative element. Hence the double bond character, the chances of getting double bond character are less in D. The bond between C and O is D, so the double bond character chances are less. So single bond character chances are more, hence T would be having more bond energy, more bond length than A and B, because A and B are actually having equivalent RS and they will be equally having a double bond character, unlike in D. And those two would be more than C, because as the conjugation between this lone pair and pi bond is not happening, hence this bond between C and O will retain its double bond character to the maximum possible limits. Okay, so this would be the order. Okay, so this ends our lecture. So we'll meet in the next lecture. Till then, good luck and goodbye.